Well, finally, we get to see a circuit that has something other than resistors connected to the operational amplifier. In this case, the circuit we're going to look at is an integrator. In other words, a circuit where the output voltage is proportional to the integral of the input voltage. Here's the circuit, and topologically this is essentially identical to the inverting amplifier. Before we do the analysis, however, let's talk about the compensation resistor connected to the non-inverting input. It has a value of R. Now, you might be thinking, well, wait a minute. In the case of the inverting amplifier, we had to put both the input resistor and the feedback element, which was a resistor in that case, in parallel to determine the thing connected to the non-inverting input. Why aren't we putting the impedance of the capacitor in parallel with R to determine the compensation component? Well, remember, we are trying to compensate for the input bias current. The input bias current is essentially a DC current, a frequency of 0 in other words. Now, the capacitor to DC looks like an open circuit. Thus, as far as the DC bias current into the inverting input is concerned, the capacitor just looks like it's not there. It's an open circuit. All that input sees is the input resistor R. Thus, the compensation resistor also is simply R. Okay, let's talk about how this little puppy works. And just as in the inverting amplifier, the current through the input resistor is V sub I over R. All of that current has to go through the capacitor since it cannot enter the inverting input. Now recall that the VI relationship for a capacitor is given by capacitor voltage as a function of time is equal to 1 over C times the integral of the current into the capacitor with respect to time. And if we cast this as a definite integral, let's say from 0 to some time t, then you've got to have the constant of integration, which is essentially the voltage across the capacitor at time 0, or whatever you specify as the lower limit on that definite integral. But now, remember, the current into the capacitor is V sub I over R. So you get 1 over C times the integral of VI over R dt plus your constant. But you can pull the 1 over R term out, and then you've got V sub C of t is equal to 1 over RC times the integral of V sub I dt, plus, of course, your constant of integration. So now we have something, the voltage across the capacitor, which is indeed proportional to the integral of V sub I. Now we could dink around with the values of R and C and actually make it 1, but in general that's not really necessary, and sometimes it's really inconvenient for a variety of reasons to try to make it 1. You can, if you really need it to be 1, you can compensate for that later on. Now there's one final little problem here, which is, note where the positive reference on C is. We've got a virtual ground at the inverting input. Now remember, we've got that little compensating resistor on the non-inverting input, so you say, well, wait a minute, it's not going to be exactly ground. No, maybe not, but if we assume that it really is a virtual ground, that it really is an ideal op-amp, and depending on the op-amp, it may be really, really close to a virtual ground, but we can, in general, treat it as a virtual ground. Therefore, V out is the negative of that voltage. So we've really got V out equals minus 1 over RC times the integral of VI dt. If the minus is a problem, we could, of course, invert that. If the 1 over RC term is a problem, we could follow it with the appropriate amount of gain to deal with that. But basically, here is our integrator. Later, we will see some circuits that use the integrator as part of their function in a larger structure. And in our next video, we will look at this same identical circuit from a slightly different perspective, not in terms of doing an integration, but actually looking at this in the frequency domain, which means, of course, that we've got to replace C with the impedance of C. But that will wait until our next video.